Okay, so let's go back to that first function we had, f of x comma y equals 2x plus y minus 4. And, let's think about what would happen if you just kind of on your own draw the level set for output 2 and then draw the level set for output 3 and draw the level set for output 4. What would you be looking at? And I hope in the end you would see you'd have the lines y equals negative 2x plus 6 and then negative 2x plus 7 and then negative 2x plus 8. You got to work out the algebra. It's not so bad. But along with the earlier line we had y equals negative 2x plus 5, how would you describe all these lines? Right? These would be a bunch of parallel lines. And so let's just see a picture of several level sets all together by clicking on this link. Okay, so it looks like this, right? So for that function, this level set, it's not as complicated as the kind of wacky function we saw a moment ago, but here's the level set for output 1, here's a level set for output 2, here's a level set for output 3, here's a level set for output 4. Here's what's nice about this is that when we looked at the graph of this function z equals f of x comma y, yeah, okay, it was kind of nice, right? Because it was just a plane, it was flat, unlike the other more wavy thing that we've seen in purple for some of the other f of x comma y's. A plane is fairly easy to deal with, but even a plane, it's just hard to draw and depict and to get information from, and that's three-dimensional. So instead, what we've done here is, the fact here like this where k equals 3. So let's take a look on this. We have like when x is 2, y equals 2, that ends up on this line where k equals 3. So what this is trying to tell us is when you pick the x input to be 2 and you pick the y input to be 2, that's going to calculate to being z, or the output being 3. And so all of the points along here are examples of that. So when you pick x equals 2.5 and you pick y equals 1, again, you're going to get the z coordinate to be 3. And so all of these, you know, all along this slanted line k equals 3, this is depicting all of the places in a 2D world. We're able to depict all the places where if we did graph the function, which again it was nice enough because it was a plane, but all of these places would have a height of 3 or z coordinate of 3. Unlike over here, this furthest outline, that these are showing all the points x comma y where the height would be 1, and by height I mean z coordinate. Now, instead of drawing a graph, which is three-dimensional, and it was among the nicest possible three-dimensional graphs of functions we could get. It was, in the end, it was a plane. What we did was we drew several level sets in two-dimensional space. This is nice. It's one dimension lower. Instead of one three-dimensional picture, we had many two-dimensional pictures, right? By many two-dimensional pictures, I mean there's these 4 separate lines. So 4 separate two-dimensional pictures which we could still all draw on one piece of graph paper. That just worked out, I think, a lot nicer because it's one dimension lower. So a collection of several level sets drawn on the same set of axes, as we just saw here, is called a contour map. If you only had a contour map, can you sort of see the graph of f in your mind? Can you see like all of these points here? So imagine, let me kind of zoom a little bit here, like where this origin is, like right where my mouse is. Imagine, I know you're looking at this on screen, right? But imagine right here, there's an axis that's popping straight out of the screen, right? Like perpendicular to the screen, or rather there's this z-axis pointed straight towards you, right? It's the normal vector to the plane of your screen. And so with that z-axis pointing towards you, you've got the bird's eye view here. Can you imagine all of these points along here popping out towards you, 1 unit, and all of these points here where k equals 2 popping out towards you 2 units, and all these points here on the line labeled k equals 3, those points all have raised towards you 3 units, and so on and so forth. So with that, can you sort of see the graph of f in your mind, right? And then let's click on one more link here. Okay, so what you're seeing here is that earlier wacky function that you saw the graph of in purple. What I've done now is I basically took existing code that I had and I just made copies of sliders, and I just had to change the label. So here's, a level set shown in red for a specific, so fix an output value, and then there's a depiction in red of all the inputs that achieve that output. It's really just a picture in red here in this two-dimensional space of where this plane intersects this purple graph, and then just for a different output, so instead of K, I just used the next letter L, right? And so, when we're talking about output 5.8, what inputs lead to that output? So in the graph where we should naturally talk about it first, it's where does this blue horizontal plane z equals 5.8 intersect the purple? And it doesn't look like it does here because it's too high up. But if I maybe zoom out, I don't know if I'm gonna make the computer crash doing this. There, I've zoomed out a little bit. Yeah, it eventually does indeed intersect the purple, and it's hard to see all this, stuff of this plane intersecting this purple wavy sheet-like thing, this surface. So we're seeing just that intersection, like from here on the XY plane shown in blue here, and then here's another level set. So it's nice to actually, in a sense, see several level sets all together. Let me try to pick numbers in order. Like, how about k equals 1-ish? It's 1.2, sorry. And then the next k value, or L, how about close to 2, 2.2? And then M is, say, 4. I don't know, right? But you see over here, let's see, red, then blue, then orange. And so you see in the picture on the right, the red plane, and then above the blue plane, and then above the orange plane. And so let's say you didn't have this picture on the right, which would be really difficult to have any hope of generating on paper. And here, at least, I'm not saying that this picture on the left would be all that much easier to generate based on how wacky the formula for the function is, but can you imagine just seeing this picture here and then having all of the points that are in red jump out towards us 1.2 units? Because again, the z-axis is pointing straight towards us, right? And then all of the points in blue jumping out towards us 2.2 units, and all the points in orange that are shown here jumping towards us exactly 4 units, because M is 4, right? Then that starts to give us this picture from up here, so to speak. I think I need to rotate this around a little bit, right? But, and sorry, I think because of how I zoomed, this is not centered, but I hope you can kind of see the information just in here. There's a 2D picture of like little moments of what's going on in the 3D picture. Okay, just to make sure we're on the same page, yeah, that link that we just clicked on, it shows a contour map. Contour map just being fancy for saying several level curves for the purple function from earlier, right? You can change the values of the sliders as we did. Why use contour maps, or why use level set? Okay, contour maps are just several level sets. So why use contour maps, or why use level sets? It requires fewer dimension. So think about it. Earlier we looked at a standard Calc 1 style function, 1 input, 1 output. And so, yeah, the graph requires 2 dimensions because 1 input plus 1 output meant 2-dimensional space. But the level set only used input space. And since the input was 1-dimensional, there was just x, we just needed the x-axis. 1-dimensional level sets, 1-dimensional contour map. You can, on one x-axis, you can draw several different level sets if you just draw those level sets in different colors. Now, when we looked at a function f of x comma y, there's 2 input variables x and y, and there's 1 output variable z. And look, the graph requires 3 dimensions, and that's just hard. It's harder to draw in 3 dimensions. And we were just talking about a plane here, which is, fairly okay to draw, and things could just get wackier when you don't have something so nice like 2x plus y minus 4. If you had like sine of x, or like y to the third, or whatever, right? So a level set only uses the input space. So since the input here is only with x, the inputs are x, the x coordinate and the y coordinate, you'd only need 2 dimensions to draw something involving just the inputs. So that a level set, drawing a single level set, so fix a z value, well, that's a fixed z value. So you only need to deal with x and y now, right? Only 2 dimensions, xy plane. And if you draw several level sets altogether, that's again called a contour map, and you draw each of the level sets, say, in a different color, then that's only going to require 2 dimensions.